Australian Institute of Physics and the University of Adelaide. Speaking today is Dr. Paul Jackson from the University of Adelaide and the Centre of Excellence for Particle Physics at the Terascale. Paul's also part of the ATLAS collaboration, working at the Large Hadron Collider. Paul graduated in 2004 from Victoria, Canada with a PhD. He has had research positions at Ohio State University, the University of Rome and Stanford University, and moved to Adelaide in 2011. He's a lecturer in particle physics here at Adelaide, and he's going to tell us all about the very exciting news about the Higgs boson.
Okay, 2 seconds to get started here. First, thanks very much for the overwhelming response to the public lecture. We'll see if we can make it as interesting for you as obviously you hope it will be. So front lights off, main lights off. And you're obviously going to make some close friends tonight because everyone's packed in pretty tight. So what we're going to be talking about tonight is the search for the Higgs boson at the Large Hadron Collider. But I want to actually frame this in the context of the experiments that we do there. What I'm showing on this first slide that I have are some of the images that we've taken with the ATLAS experiment that Pvalue mentioned I work on at the CERN Large Hadron Collider. And we'll come back, hopefully throughout the course of the next hour, to explain what some of these pictures mean, explain how we get them, and how we can use these to try and disentangle the measurement of some fundamental physics. So really that's the kind of journey that we're trying to go on. So to start this off, I want to embed this in the context of what particle physics is. So the aim of particle physics, or we'll also call it elementary particle physics or high energy physics, it's really two questions. They're quite simple in a sense. What is everything made of? It's one question. And what holds it all together? And so really these are the two fundamental driving aspects of what particle physics is trying to accomplish. And to a certain extent, we've actually done a lot of this already. We have a very good understanding of the particles that make up the universe. There are 12 of them. They can be separated out, the matter particles, into quarks that I've shown here in blue, and leptons that I've shown here in a slightly faded yellowy color. And there are forces that act on these particles. For instance, the weak force, which is responsible for radioactivity, is propagated by two particles called bosons that we'll come back to a little bit later on, called the W and Z boson. And this acts on all of these 12 matter particles that we have. There's another force, the electromagnetic force, which is propagated again by a boson called the photon. This acts on all of the charged particles that we have in the picture here. So all of the quarks, which have fractional charge, and each of the charged leptons, so the electron and its two heavier cousins called a muon and a tau lepton. So this electromagnetic interaction is what's driving the mobile phone in your pocket, driving the projector that we have here, the laptop that I'm using to show this talk. One other force that acts on only the quarks in this case is called the strong force. And this is also mediated by a particle that we call a gluon. And this is an attractive force. It holds together these quarks inside, for instance, inside the proton, where we have two up quarks and a down quark. And these bind together to form the nuclei of the atoms that go and make up the whole universe. And that's essentially it for particle physics. We have these three forces that bind together the various matter particles that we have in the universe. Of course, there's one other force that you're all aware of, which is gravity. And gravity acts on massive objects, of which all of the particles of matter that we have are massive. They've been measured in the laboratory to have a certain mass. And so gravity acts on all of these particles, but at the scale that we talk about in particle physics, it's extremely weak. So it pervades all space, but it's a very, very weak force. And so we tend to neglect it in terms of particle physics, because for the size of these fundamental particles, gravity essentially is meaningless to these particles. So that's it. We have these three forces, and we have this set of particles that they act on. And this comes forth to make a theory. Essentially, we can take these particles, and we can, with recourse to mathematics, we can write down a theory that explains the interactions of all of these matter particles with the forces that bind them together. It's very simple in a sense. In fact, it's so simple it can be written on this t-shirt. I won't be explaining it so much, but it's based on a set of fundamental symmetries that we've measured. It's also extremely elegant. I mean, there's only a few terms in here, You can actually buy this t-shirt at CERN if you're so inclined. And the important thing about this theory for particle physicists like myself is that it's also a predictive theory. In fact, it's so good that we call it the standard model of particle physics. It's the standard model because it predicts a set of interactions. And every time we try to measure a property of this standard model, it's succeeded. So every experiment we've built to try and see if we can break this standard model, see if we can understand something else, it's actually succeeded. And the predictivity of this model is actually won out. There are some issues with it, though. And the one issue that has been a problem up until now is that there's a fundamental particle that we hadn't seen so far, the Higgs boson. And this is part of the theory that is now, hopefully, we believe, complete. But there are also some further issues with particle physics that this theory cannot explain. And I've got to just step over here because I've got to start this video, which I can't do with my little device. But what we see in these 4 pictures that I've put up are a variety of experimental observations, in a sense, from cosmic rays bombarding the Earth with very, very high energies that we can measure, from the collision this is the bullet cluster, so a measurement at the scale outside of our solar system of a collision, which gives us evidence for something called dark matter, and then a measurement of the age of the universe and also a mapping out of the mass and matter of the universe, which shows that these particles for our standard model are only a small aspect of the entire universe. Now, the video that I'm showing to the upper right here is actually a collision that occurred within the Atlas detector. So this is 2 beams of particles colliding at the center of the Atlas detector and producing a slew of subatomic matter that we can then go forth and try and analyze. And actually, this particular collision is interesting because it's one of the data collisions that we did, reconstructed obviously as an animation, but this is one of our potential candidates for a Higgs boson. So this fabric of the universe we understand really well. We have, from ourselves down to atoms, is about the same order of magnitude as going from atoms down to quarks. So these quarks are extremely small objects. And what we're really trying to do with this Large Hadron Collider that I'll come to discuss in a few slides' time is attempt to understand why the world looks the way it does at this fundamental subatomic level, and what are any missing pieces to this puzzle. So I've alluded to some of these already, and we'll come back to this in a bit more detail later on. So what do we need to be able to accomplish these questions? It's the first thing we can ask. And I'm going to split this into 4 things that I suggest we need to be able to do this. The first is accelerators. These are powerful machines that are capable of containing and accelerating particles to very, very high energies, very close to the speed of light, and then bringing them into collision. When we collide these, we need a set of detectors. So big, complex instruments that are able to measure and record the particles that stream out of these collisions that occur when we collide these beams together. So when we have this huge amount of data coming out, we need a vast array of computers to be able to collect, store, and ultimately distribute this data for analysis around the globe. The reason why we do this is because we also need a huge number of people working on this. There's a vast amount of data that requires an enormous number of scientists, engineers, and technicians to run these accelerators and detectors, and also a huge number of students who are able to exploit the data that we're getting out of these detectors. So I'm going to touch on each of these 4 things and sort of allude to how they're going to be useful for this potential discovery that I'll get to at the end of the talk. So the accelerators. That's the first most important part. We've already seen one video of these. They're essentially pretty simple things when you think about it. You want to get 2 objects, smash them together, and have this person taking a picture. There's pretty fundamental discrepancies with this picture. Let's face it, that these 2 people look a bit scared because they're going to get glass in their face. But this is the essence of what's going to happen. We're colliding objects together and then looking at the remnants of what happens afterwards. So we do this at the Large Hadron Collider, or LHC. This is based just outside of Geneva in Switzerland at the CERN laboratory in the shadow of Mont Blanc here. And to put this in scale, this is the runway of the Geneva airport. And this entire diameter of the accelerating ring we have is 27 kilometers. So what it consists of are two beams of counter-rotating protons. So these protons are going extremely quickly. It's 100 meters underground to shield us from any background radiation from the atmosphere. And we're essentially trying to recreate the conditions billions of a second after the Big Bang. So this is essentially when people talk about this being the Big Bang collider, this is what they mean. We're actually trying to go back in time, in a sense, to recreate these conditions that we had. And after making these collisions of protons, we have a pair of multi-purpose detectors which are exactly on opposite sides of the ring here. And we bring these protons into collision in the center of these detectors, as I mentioned just a second ago, and try and exploit the very high energy collisions. So at CERN, this Large Hadron Collider is essentially the fastest and most brutal racetrack in the world. This guy obviously isn't on the racetrack. This is just someone who's checking around the ring right now. And he's probably in a lot of trouble if there's some beams in the machine, but I assume there's not. So what we have are these bunches of protons, collections of protons, several thousand billion of them, and they're racing around this 27-kilometer circuit at 99.999999% the speed of light. And then you crash them head on, and you record what happens. And you're doing this 40 million times a second. So that's how you collect a huge amount of data. And you need this to be able to look for rare processes. But this collider is also one of the emptiest spaces in our solar system. This is a picture of a 15-meter-long cryodipole. There's about 1,200 of these around the LHC ring, along with some additional bending magnets and focusing magnets to be able to keep the beams contained. And this beam pipe is evacuated to the same vacuum as essentially interplanetary space, with a pressure of about 1/10 the surface of the moon. So the big and small numbers continue. It's one of the coldest places in the universe. It's only about 1.9 degrees above absolute zero. This is colder than interstellar space. This is required to get you the superconductivity and superfluidity you need to be able to actually contain the beams and then accelerate them to these remarkable speeds. But simultaneously, it's also one of the hottest places in the galaxy. When the reactions occur, they're extremely violent, ripping these protons apart, and they correspond to temperatures 1 billion times higher than in the core of the sun. And that's roughly this very big number. So what you can see with these collisions is that we're creating, for infinitesimally small amounts of time, these very, very hot, dense regions where we're looking for these remnants of what happened in the early part of the universe. So how can we accelerate these particles? I mean, I'm not going to put too many equations in here tonight, but one that I think we're all familiar with is E equals mc squared. So Einstein taught us many things, but he taught us that energy and matter can essentially be interchanged. So we can trade this kinetic energy, the energy of motion that we have put into these protons, for the creation of mass energy, in a sense. So what this means pictorially is a colliding of protons here on the left-hand side is able to produce, after this collision, a pair of the heaviest particles that we've ever measured so far, which is the heaviest quark, called a top quark. So by just recourse to E equals mc squared, you can see by putting more and more energy into this collision, we're able to create more and more massive particles. And that's essentially what we mean by the Large Hadron Collider being a discovery machine. We have a huge amount of energy we're putting into this to really probe and see if we can make something quite massive coming out at the end. So another quick aside, not really an equation, but just to mention what an electron volt is, since I'll be coming back to talking about this. So an electron volt is the kinetic energy that's gained by an electron when it's accelerated through an electrostatic potential of 1 volt. So there it goes through this thing, and that's 1 electron volt when this electron is accelerated through that. So again, we come back to E equals mc squared, and we can quote the mass of subatomic particles in terms of this essentially energy variable. And so what we see for a proton, for instance, that's going to be an important aspect of the talk, since we're colliding these, a proton has a mass of 1 GeV, so 1 billion electron volts. And the energy of the beams in the Large Hadron Collider are on the order of TeV, so 1,000 billion electron volts. So you need to put a huge amount of current into this machine to be able to get up to these types of energies. So this Again, you're not supposed to take this away in any real way, but just to show you the accelerator complex at CERN, and that it's not simply just the Large Hadron Collider, which is this big guy here. You need a set of additional booster accelerators and then containment rings to be able to get your protons into the Large Hadron Collider with the quality and criteria that you need to be able to accelerate them up to the fractions away from the speed of light that you're hoping to achieve. So I have another video which I don't think starts here, so I've got to come back. So this is going to show, again, a little bit similar to what we had earlier, but just to frame this in a bit more detail. This is basically pictorially seeing what's happening when we have protons going around the Large Hadron Collider. So we can zoom inside the beam and see the 3 quarks rattling around inside the proton as they move towards one of the detectors. So in this case, this is Atlas, and we have the 2 protons, one coming from each direction, that collide in the center. So this is what I was saying happens 40 million times a second. We have these collisions of protons, and we get these remnants that are spewed out into our detector that I'll talk about in a second. Now, what's particularly interesting about this one is you can see we're focusing on these 2 legs and the 2 green blobs. And this particular event, as we call it, is consistent with a Z boson, the propagator of the weak force, you'll remember we talked about earlier on, decaying into an electron and its antiparticle. So we're going to use this property that a particle will decay into other visible objects within our detector to be able to then reconstruct all of these types of decays that have happened and get a better handle on exactly which ones have occurred like this. We'll do the very similar thing for the Higgs boson. The Higgs boson has characteristic decays, and we need to collect all the events or collisions that contain those decays and then try and reconstruct those all together in one go. So we do this with a set of detectors. This is a picture of the Atlas detector while it's under construction. You can see this hole in the center is where the beam pipe is going to go. So this is where the beam is coming in and out of the screen here. And we're missing a big chunk in the middle because this is during the construction. And this guy's becoming quite famous because everyone likes to show this picture now. But the large pieces on the outside are the outermost parts of the detector, which are called our muon system. And I'll mention that in a couple of slides. So the collaboration itself is a huge enterprise. It consists of some 38 countries and about 178 universities. So this means there's about 3,700 physicists working on this experiment. And that includes on the order of 1,000 PhD students, all of which we managed to keep very busy somehow. The important part, obviously, is Australia. And so we want to focus on that for today's talk. And the Australian involvement is focused through a centre of excellence called COEP, the Centre of Excellence for Particle Physics at the Terascale. And that includes 3 universities, Adelaide, and then 2 others. So obviously we care mostly about it. And yeah, there are a lot of countries here, and we collaborate with a huge number of these guys. So every single continent involved, and it truly is a global enterprise in physics research. So to kind of set this in scale, we talked already that it's 100 meters underground where the accelerator is. But to get an idea of the magnitude of this thing, it's actually 25 meters high, which is about a 5-story building, and 44 meters long. We have a couple of people who volunteered to stand on the end there just to show you how big it is. And it's essentially like an onion. There's different layers as you go further out from the interaction. So your beams are coming in here from either end, just as our simulation showed, and they collide right in the middle here. And we have these various layers of sort of like Russian dolls, the different layers of things as you go further and further out. And each of these different parts of the detector has a specific job to do with trying to measure each different type of particle that we then try and bring all together when we have these collisions to try and understand exactly what's come out of the remnants of these. One of my favorites is our 87 megapixel camera, as I like to call it, because I worked on helping to build this. So this is 3 different parts of the subdetector, and it's the first thing that the particles see when the beams collide to produce things. So it has to be very, very radiation hard and very, very capable of measuring everything that happens. Now, I call it a megapixel camera because essentially that's what it is. It has a set of pixels. The resolution's very good. Okay, 1/7 of a human hair, that's pretty good. But everyone's got a phone in their pocket that's got a camera on it now. Your iPhone is an 8 megapixel camera. So this is only 10 times better than that. So, okay, you got your iPhone at Crazy John's or Vodafone or wherever you go, and that didn't cost you a lot of money. So why is this so special compared to that if it's only a factor of 10 better? Well, one of the big things is that it's in 3D, of course. So we have 3 dimensions, and if you recall, going back to the earlier part, we're taking 40 million pictures a second. So that's really where the problem comes, if you like, that you have to be able to read these out very quick, something that we're working on here in Adelaide to improve for the future, and you've got to be able to measure this at a very, very, very high rate. So that's really, the analogy to the camera is a true one, but the enormity of the task for this particular apparatus is quite difficult. If you move a bit further out, so I've grayed out now this megapixel camera, and we've got a thermometer just outside of that. So the thermometer basically measures the energy. It absorbs the energy or heat that these objects are giving off as they go a bit further out of our detector. You don't need to care so much about all these different things. There are 2 different parts to it. An internal bit that's called an electromagnetic calorimeter. This measures electromagnetic objects. So an electromagnetic object is like an electron or a photon. And then outside of this, we have another calorimeter called a Hadron calorimeter that tries to absorb the energy of everything else that makes it out of there. And that's really essentially what they're trying to do. Outside of this, there's a muon system that measures these muons, heavy versions of electrons, and that's your lot for the detector. So what we can do is try and explain what happens when we take these snapshots. We create this debris from when we collide the particles together. This is left over from the collisions, and as I've tried to mention, we do this in 3 dimensions. It's really, really fast. So how can we point this out? Well, I like to, again, this guy, to try and make it look bigger, he's standing on a little box there, but I don't think that makes a lot of difference. It's still a huge piece of detector. So if we just take a little pizza slice of this and take a look at what happens when you have particles coming into your detector, you can start to get an idea of what we're doing when we have these collisions. So this innermost part, this is the megapixel camera, these first bits that we see after we have a collision that happens at this circle here. This is immersed in a magnet. So inside a magnet, any charged particles that are passing through are going to bend. So we're able to measure how much they bend and essentially where they hit these different bits of the detector, and we can measure their position and their momentum, and that gives us an idea of what type of particles they are. So I mentioned this electromagnetic calorimeter measures electrons. They're charged particles, so they'll have a track that's come through here as well from some hits. And then a photon, which is not a charged particle, so won't have a track there. So you can distinguish between these photons and electrons. The hadronic calorimeter is absorbing all the energy of the protons and other particles that are formed by the quarks going into our detector. So we're able to pick all of these up, and then the muons pass all the way through, happy as they like, and they get measured in the outer part of the detector. So they don't interact with these other, or they interact very, very weakly with these other parts of the detector. So this is really what we're doing. These are the building blocks of what happens when we collide the protons together. And we do this a huge amount, and then try and disambiguate the types of interesting processes we're looking for from the types of somewhat more rudimentary, boring things that we see when we collide these things very often. So just dissecting what this image looks like a little bit, this is an actual image from the data in the ATLAS experiment. So you're kind of looking head-on to the detector here. This is where we collide the beams. And imagine you just took a slice right down the middle of it, so we could just cut it open and take a look as if it was a piece of cake or something like this. And what we see is the kind of things I was pointing out. In this middle bit, these different colored lines are all charge tracks coming from charged particles that have been produced after our proton collision. So that should say that. And then we get, I must admit I didn't see this, but there is a very faint red line that goes through here. That's a muon that is passing all the way through our detector and that we measure in our muon system. So this is a heavy electron that's passing all the way through our detector. And then we get these 2 clumps of particles you can see here and here that are these jets of particles that are measured in our calorimeter. So this thermometer is absorbing the energy of all of these particles, whether they be the electrons and photons in the electromagnetic calorimeter, or these jets that the quarks form as they pass into our outer reaches of the calorimetry system. And so this is what we use. Now, if you remember back to the video that I showed a few seconds ago, I kind of suggested that we can try and understand the particles that we're seeing through their decays. So trying to see a specific particle through its decays. And that's what these graphs are showing. I don't want to scare you with too many graphs. But essentially, what we're showing on the y-axis of this is the number of events. So the number of times we've collided protons together, for instance. And then on the x-axis here, for the right-hand plot, is the mass of taking two pairs of electrons, an electron and its antiparticle. So this is exactly what we showed in this video a little bit earlier on. And you can see, as the mass increases, there's a variety of different structure that starts to pop up as you take a lot of events of this type. And what you can see is evidence of, in particular here, a Z boson decaying to two electrons. So this is essentially what we're doing here. We're able to see these peaks of different types of particles by collecting a lot of events of a certain type and then analyzing these all at the same time to look for these specific characteristics. So it's this type of thing that we're doing when we look for any new particle that has a resonance, that has a peaking structure in this type of variable. You want to find a variable, whether it's the mass of your two guys that you've made, or something else that has a specific peaking structure over what this falling distribution is essentially the background to this. So the background is any other types of processes that have given you these two same charged particles, but don't exhibit this characteristic of having come from this particular resonant state. So this is something that you should try and keep in mind for a bit later on. So I mentioned also computing as one of my 4 fundamental things that we need to be able to do these experiments. The LHC has gone the wrong way and analyzed essentially all of its data on one of the most powerful computing systems in the world. So we call this the grid. What this means is that given our detectors spew out analyzed data, so this is pre-processed data, on the order of a gigabyte a second, we need to be able to process this and split it to a lot of places where everyone is able to access this as quickly as possible. So this is on the order of 30,000 Encyclopedia Britannicas a second. So per year, if we were just to say, well, we'll put it on CDs and mail it out to people, that'll be fine, that'll work. We're going to get a stack about 20 kilometers high of normal CDs. So that's, 4 times or so the size of Mont Blanc. So that's going to mount up after a few years, and you're going to run out of CDs. So that's going to be quite difficult. So we have to somehow find a way of dealing with this 15 million gig of data that we get from these experiments, each of these experiments producing this. And what we have is this computing system where CERN is able to process the data at a very fast rate and spread it out to a set of different computing facilities based all around the globe. And we have one in Australia as well, where we are able to choose, in essence, which data we think is interesting, which subset of these types of events we'd like to analyze, and we can keep those at our specific computing facility and then have faster access to that stuff. Of course, there has to be some interplay between all of these, because we can't all say we want to look at the same Higgs data and nobody else keeps the other stuff. We have to all play fair with each other. So I mentioned these accelerators, detectors, and computers, and I started asking myself why when I was halfway through this talk, because I realized I hadn't covered this at all. I mean, it sounds quite fantastical to build these big machines and to build the big accelerators and do the difficult computing. There are a lot of reasons why. I mean, from the particle physicist perspective, it's really to understand the fundamentals of nature. But there are always very important spin-offs of this fundamental research, and it's always been a driving force for innovation. You can take this from a sort of historical context, from basically looking at something like relativity, which of course was a groundbreaking theory discovered by Einstein. And this is now crucial to the GPS system that you might have used to get to the Kerr grant today, or that will get you home later on when you're thinking too much about the Higgs boson and aren't paying enough attention to the road. Then electromagnetism, which I mentioned earlier, is driving the telephones you use with the electromagnetic waves you have when you just texted "I hate physics" at Kerr grant to your friend or whatever it is. This is what happens. So you actually were using a bit of physics at that moment of despair. So, of course, to bring it back to the actual things that I was talking about, the accelerators, detectors, and computers, there are it's not really spin-offs, but there are also use cases of the technologies that people are coming up with. Far more than half of the accelerators that are developed in the world are used in hospitals these days for Hadron therapy. This is a growing industry for treating of tumors, among many other things. So this accelerator physics is finding employment, among other things, for a lot of people, but also very, very good use case within the communities. And also detectors can be used not only for cases like defense and a variety of sensing, but also for other good things such as positron emission tomography in hospitals. I hope you're all pretty aware that the World Wide Web was invented at CERN by particle physicists as a way to stay in contact. So that's quite useful. This guy was quite fundamental in doing that, and I updated his thing so he's checking Facebook these days instead of the first web page he had on it. Oh. But this was really a communication tool that was come up with by physicists as a way of being able to spread information, initially between Europe and the United States. So with all of these things in place, I touched on the accelerators, the detectors, a little bit about the computing. I've kind of just briefly glanced over the fact that we have a lot of people working on this stuff. I'll mention how this kind of ties together to look for the Higgs boson. So these are a set of pictures that I really like, but this is what you'll find if you look up Higgs boson particle in your favorite search engine. You get a variety of different things. This is an event display from the CMS detector. This is Peter Higgs hitting two blackboard cleaners together. And this looks like a load of white hair around the pit of an avocado or something. But I particularly like this one because it really shows, actually, in a sense, what's happening when you try to collide these protons together. The protons are objects that have internal structure. When you try and collide these bunches of billions of them together, you get one or a few collisions that will produce some interesting physics coming out of that. So this is really actually kind of hitting close to the mark of what we're going to talk about. This one's a black hole, I guess, so I think that's not really particularly related, but it's a nice picture, so I use it. So the Higgs boson, just to kind of set a little bit of context of what this is, and why it's been something that people have thought about for a long time. This was first written down as a theory by Peter Higgs back in 1964. And the paper that he sent to the journal was initially rejected. It's not a well-known fact, per se, but this is it. This is the paper that he sent in 1964. This is what he wrote. If you're feeling underwhelmed, I must admit I was when I first checked this out. I thought it was going to be many, many pages of earth-shattering physics, and it's a page and a half. It's extremely concise and very, very clear, but it's a page and a half of stuff. And there's follow-up papers that explain things in a lot more detail, but this is the basic first thing. And he wasn't the only person who came up with this. There were a variety of other physicists, all in about 1964, particularly Braut and Engler, who came up with very, very similar theories. And this essentially became known as the Higgs boson just because it stuck as a catchy name, I think. He was also, I believe, the first one to get his paper in the journal by a matter of days or hours or something like this. But the idea is also based on groundbreaking work by many other people, Nambu, Goldstone, Anderson. These are famous guys. So I've got a couple of pictures of Peter Higgs, if you don't know what he looks like at the top. This one I particularly like because he's visiting Atlas, which is very good for us. But I do love the expression on his face in this picture because you get this mixture of awe and fear on his face that he seems really excited by the fact that there's this huge experiment but then sort of, well, what if I got this wrong and you guys have just spent all this money and built this thing and I forgot to carry a 2 somewhere and it's just all rubbish. So he was certainly very, very amiable for toward the physicists at the experiment when he came to visit Atlas, in any case. So one other thing I'll touch on before I get back to a little bit of physics is the God particle. Because obviously everyone calls this the God particle, so maybe you don't know where that came from. This actually arose from a gentleman called Leon Lederman who wrote a book in 1993 that became titled The God Particle. What is this? If the universe is the answer, what is the question? Is the subheading for this. Leon Lederman's an extremely famous physicist. He won the Nobel Prize in the late 80s for his work on neutrinos, among many other things he's done. So the reason for it becoming called the God particle, this book, there are 2 quotes for this. One that I think he probably got asked quite early on. He said, because it's so crucial to our understanding of the structure of matter, and yet it's so elusive that you have to call it the God particle. And it sounds quite beautiful until the day after or something. He said, well, I wanted to call it the goddamn particle, but the publisher wouldn't let me do that. So we had to call it the God particle. He thought the goddamn particle would be more appropriate given its villainous nature and the expense that it's causing. So I think both of these are equally right, but most particle physicists really don't like the term God particle, but I don't mind it too much. It's nice and catchy. So this is a diagram of how long it's taken from the theoretical idea of a specific particle within the standard model. So, as I said early on, we've measured all of these particles in the standard model now of particle physics. And now we've hopefully measured the Higgs boson. And you can see that the amount of time it took to measure this particle is on the order of 50 years. And essentially this was to get to a point where our technology had advanced to the level where the theory was to be able to build a machine that was capable of making this and measuring it. As I've also said, even with this wonderful documentation of all these particles within the standard model, there's extremely compelling evidence that this is just a sliver of the overall content of the universe. And so building a very high energy collider that could in principle give you access to this unknown quantity called dark matter, or heaven knows, give you some inkling of what this enormous swath of what's called dark energy is also a reason why we call the LHC a discovery machine. Potentially we could have some access to these other pieces. So coming back to the Higgs, the Higgs field and the Higgs boson has a relationship with mass. So essentially, things get massive by interacting with the Higgs field. So it's like an ant walking through treacle. The matter of the universe sticks to the Higgs field. This creature's walking through the treacle and getting heavier and heavier as it goes through there, depending on its own mass. If it's very light, it can skim over the top and not really pick up a lot of mass. So in our cartoon here, the electron is feeling light as a feather because it's not getting a huge interaction with the Higgs field. The Z boson feels a little bit like I do sometimes, that it's let itself go and it's really bloated and it's getting really heavy. But without this Higgs field, without this Higgs particle, all of the particles in the universe, so all of these matter particles that we talked about earlier on in the standard model, they wouldn't actually gain mass. And so the universe that we have would exist, but it wouldn't form the structures necessarily that we have to make galaxies and stars and the bigger scale structures that we see in the universe. So in essence, the fact that each of these particles is given a specific mass by its interaction with the Higgs field, and as a consequence, we can see the structure and the life that we see in the universe today, actually makes the God particle analogy not such a horrible thing. It's really quite a fortunate thing that this happens, one would imagine, but it happens nonetheless. And I like to make the analog of it being the DNA of the universe, because essentially each of these particles, they get their fundamental mass from interacting with this field. They interact with the Higgs boson, and how much they do that tells them how massive they are. This Higgs field's everywhere, and every single particle is told how massive it is. So just as your DNA gives you specific characteristics, this Higgs field, when it interacts with a given particle, tells that particle its characteristics. So In the last bit, I'd like to touch on the actual measurements of this, so how experimentalists can go about trying to measure this particle, if it exists. This is the Atlas experiment. This is the control center of the Atlas experiment with a big mural of the detector. The detector, as we talked about, is 100 meters underground. But this is where we do the work. So to do another analogy of the amount of work we have to do to try and pick out these events, if we analyze all of the last 2 years of data and represented them as grains of sand, they'd fill an Olympic-sized swimming pool. And given that we have an Olympics going this summer, I thought this was a good thing to talk about. So the challenge then is trying to pick out a few grains of sand from a swimming pool full of sand. And that's obviously tricky to do, right? And you want to do this quite quickly because you have all of these events coming all the time. You're getting 40 million of these a second. The beams of the LHC are traveling around the ring 11,000 times a second. So you need to devise very clever ways to distinguish interesting and boring sand, or interesting and boring events, and do this very quickly. So if we go on to the next page here, this is what I've tried to show. So we're collecting this huge amount of data, and the job of the experimental physicist is to analyze it, and analyze it as accurately and quickly as possible to say exactly what's happening. But we're looking for rare processes, okay? So how do we go about finding them? So I've made this very simple graph. We measure something, whatever it is, and we have a number of times we measure it. Okay, this can be anything you like. And we have this kind of background that we saw before when we were talking about looking for the decays of objects into two different things. We have background processes. And these are coming from all the kinds of things that we could imagine in a detector. You mismeasure something, you just have other processes that look somewhat like what you're trying to look for. And what you need to do is come up with pretty smart ways to try and reduce this as much as possible. So we need to remove this noise by making these clever cuts, such that we can get down to a situation like this, where we've got rid of the bad sand, and we start to see these nice grains poking out at the top where we can actually see the types of events we're looking for. So this is the job that we're essentially trying to do, trying to characterize and understand these background-like events to be able to remove as many of them as you like so that you can get down to the bottom. And that's basically what we've done with the Higgs boson search. You see we have a background-like shape. That's this red line with the dotted piece underneath it. And then in the middle, we've started to see the little peak of the signal that we're trying to pull out of there. So without being able to pull this background down, imagine this was a little bit higher, we wouldn't be able to see the significance of this peak at all. So that's really what we're trying to do with analyzing all of these data that we collect. This is obviously a bit more complicated than that. And what we're doing with these pictures that we take with our detector is trying to understand exactly what the remnants are. So the LHC has been running incredibly well this year. And what we've done to give us a better chance of being able to measure the Higgs boson, or even find it, should it be there, is increase the energy from 7 to 8 TeV. So this is 1 trillion electron volts, it said. Okay? Well, remember the proton was 1 GeV in mass, or energy. We've also increased the intensity. So essentially, if you imagine you've got your bunches of protons, and you squeeze these so they're much, much, much smaller, and you keep colliding them, you're going to have much more successful collisions if they're in a smaller space than if they're in a more diffuse space. So we've increased the intensity of the beams by squeezing them to be smaller. The upshot of this is that it really makes our life much more difficult, in that this is what we see in our interactions. We see, instead of just one proton colliding, we see up towards 25 or 30 every time we collide the beams together. So every time, there's 40 million times a second, we're getting potentially upwards of 20 of these interactions that are happening. And so we need to not only measure the particles coming out of here, but also disentangle that they came from exactly the same vertex. And so in the terminology that we use in the detector, we call this pileup. And this really complicates the way in which we can measure the things that we produce in the detector. But we do it nonetheless. And we measure the Higgs, as I was talking about earlier on, through its decay. So what I'm showing here is, on the left-hand side, we have 2 protons. They're big and colourful. We have two up quarks and a down quark, and they're connected by these gluons, this mediator of the strong force. And so what we can do when we collide these protons together is we can actually collide the gluons that are holding them together. And this can be used in a process that's called gluon fusion. So these gluons are fusing together through this intermediate loop of some heavy particles. But they're fusing together to form a Higgs boson. And this is the production point of what we would call a Higgs boson. This then needs to be measured through its decay, as we talked about previously. And this can decay, for instance, into a pair of two photons. Now, there's sort of an interesting aside to this in that the people who followed this here will notice that we mentioned the Higgs couples to massive objects. Well, the photons don't have any mass, so how can it decay to two things that have no mass? But again, it's happening through this intermediate loop, that we call it, where there are massive particles, the heaviest that we know of, the top quark, that are able to mediate this decay. And so we're looking for evidence of these two guys produced in our detector with very little else happening. So we can look for evidence of Higgs boson decays either through these two photons, which is a very clean process, or also through two Z bosons. So you recall earlier I talked about the Z boson decaying to electrons. And so we can look for two of these in the same event, either decaying to electrons or also to muons. And then we take a look at the pictures that we made. So this is the kind of things that we see. So when we make some selection of those types of events, those types of collisions that have happened, that contain, for instance, 4 muons, as this particular picture does, you can see that there are 4 red lines that are traveling a long way out in the detector, and we said that these muons travel basically throughout the whole detector. You can also see, as I mentioned, this issue with the many different interactions, that all of these legs are coming from the same point in space. So they're all originating from the same vertex for the proton collisions that we have. And this can be reconstructed with a particular mass. And you'll recall we were doing energy and mass in GeV. So the mass of this particular object is 125 GeV. You can also look at 4 electron candidates, which if we have a Higgs decaying to 2 Z bosons, we could get 4 electrons coming out in the final state. If you reconstruct a similar thing, seeing they all come from the same vertex, you get a very similar mass of an object decaying to 4 electrons in this case. We can further look at this in more pictures. You probably guessed we would have 2 electrons and 2 muons in one case, and we get a very, very similar mass of these 4 objects when we add them together as well. So it's taking all of these different events that we've seen with this very clear and clean topology that we have in the detector and adding them together statistically to be able to see evidence of this Higgs particle. And this is what we're trying to show in this plot. So if the Higgs can decay to 2 Z bosons, giving 4 leptons, as I've just shown in those 3 pictures, we're playing the same game as I showed in that very basic diagram of us having the background and the small signal that we're trying to really pull out from this. So in this plot, what we're showing is the black points here are the data that we've collected in 2011 and 2012. So we've increased the energy from 2011 to 2012. And these colorful bumps are what you would expect for a Higgs boson signal at these different masses. So what we see is a very tiny excess here in this bump at about 125 GeV. And this is put in this table here where we expected a background of about 5 events, and we saw 13 events in the data. So we can also see what we would have expected through a calculation. As I said, we have this predictivity of the standard model, so we can calculate how many events we would expect for a Higgs boson in the standard model. And we're told that this is on the order of 5 or 6. So if you add these two together, we get about 13. So it appears that we're seeing something consistent with what we would expect from the standard model in this case. But this is just one of the ways to look for it. So we'd like additional evidence on top of that. So a couple of slides ago I mentioned that we could also look for the Higgs decaying to these 2 photons. There's a lot more background in this case because you can have a lot of different processes that look like a photon in your detector. The difference with those, of course, is that they have a very smooth shape when you try and look at the mass of them. There's no peaking structure of these. You've just measured something wrong. So you have some background processes, but hopefully you also have a signal. And what we see here is a pretty large signal where we would have expected on the order of 200 events and see even a little bit more than that for this Higgs to gamma-gamma signal. And it's also at a very, very similar mass to where we saw this slight excess of the additional lepton final states. So this is essentially what the evidence for the Higgs boson is. We're looking at these decay objects and trying to reconstruct the mass. And through these two specific channels, and the fact that I'm not even mentioning the other experiment that's pursuing very similar physics, the fact that in the same decay modes, they see very, very similar rates and very similar mass peaks as we see in the Atlas experiment. It's extremely compelling evidence that we've seen a new resonant structure of a new particle. So to put these things together, we try to say how likely it is that this has happened. How likely is it that this is just some weird, anomaly inside the data that we have? And we do this by coming up with something called a Pvalue. It's basically a probability. What's the chance that you got this right or you got it wrong? And what you can see is that at this mass where we saw some funny things happening, compared to all the other masses where you look, there's a huge dip. And you get basically it's very unlikely to be consistent with just being from the background noise that you had in your detector. In fact, it's about 1 in 3.5 million. So if you were to do the same experiment 3.5 million times, you would by chance see one such aberration. But it's essentially extremely compelling evidence that you've seen something. Also, it's less than throwing 8 die and getting 8 sixes at the same time, which is, I think, is about 1.7 million, something like that. 1 in 1.7 million. So it's extremely good evidence that something new has been found. The challenge now for the Large Hadron Collider is to pin down that this particle that we've seen actually is a Higgs boson. It decays somewhat like the Higgs boson that we expect from the standard model. But that isn't really evidence that we've seen it. What we need to do is measure all of its properties through the angular properties of these decays and see if this is consistent with the fundamental quantum numbers that this particle has. It's a very specific and very, very unique type of particle within the standard model and should be able to give us a very specific signature. And so by the end of this year, we're hopeful that there'll be enough data to be able to really say categorically whether we've seen a standard model Higgs boson or whether we've just seen a new particle. It's win-win really for the LHC. I mean, we've seen something new, whatever it is, but it would be really interesting to actually find out if this is exactly the particle we've been looking for. So, just to conclude, we discussed earlier on a little bit of what the world is made of and why this picture is incomplete. I didn't touch a huge amount on this at all, but maybe we could do another public lecture at some point. I mentioned also the instruments that we use to be able to measure these. These are the highest man-made energies that we've ever achieved and some of the most complicated technological pieces of apparatus that we've ever come up with. We rediscovered this standard picture of the standard model of particle physics. So I showed these decays of Z bosons to leptons. This is something that's been known for quite a long time now, about 30 years or so. But we had to go back and rediscover these aspects of the standard model to prove that our detector's working. And after we've done that, we can have a chance of looking for the new stuff. And it seems that we've already discovered this final piece of the standard model. But of course, given that we don't understand an enormous amount of things in the universe, and that we're very, very certain the standard model of particle physics is an incomplete theory, given that there are aspects that it doesn't cover, we're really quite certain that there'll be new surprises around the corner. And this Large Hadron Collider is going to be running for at least the next 12 years, probably up to the next 20 years, increasing in energy and intensity, which will need, again, new aspects of the detector to be built, which is going to be quite a challenge. But it's going to be delivering science at the energy frontier, precision testing some of the new things we've found, but also stretching the limits of our knowledge of the universe. Thank you.
Thanks, Paul. Now we'd like to invite Dr. Ross Young, who's also from the University of Adelaide, who's a theoretical particle physics up, to form the other half of our panel of experts who will take your questions.
Yeah.
The odds were 1 in 3.5 million, or billion, or something huge, of this being valid. But you were saying that there is so many thousands of these every second. Aren't you think that basically you've got so many experiments going that the chance of something happening going to come up regardless? What pulls it out to say that you've actually really generated the one experiment, which is 1 in the 3.5?
So that's a really good question, actually. It's the same experiment, it's just collecting different collisions each time. So you know what the collisions look like. What you're alluding to is something that statistically is called the look elsewhere effect. So if you look in a big enough range of something, you increase your chances of seeing something that has a bigger statistical fluctuation. Okay. So that, for instance, is taken into account with this previous slide that I showed with the probability value that we have. So you have to take this into account over a wide mass range to say, well, we've looked in this region, but we kind of knew we should look in this region. What if we'd have looked in a much, much, much bigger mass range? And so you take this into account, and it affects, it decreases the statistical precision of your measurement, but it only decreases it down to this level of 1 in 3.5 million, which is equivalent to what we call 5 standard deviations. Yeah.
Is there such a thing as, are you thinking or looking for an anti-Higgs boson?
That's another excellent question. So in the standard model, there's only one Higgs boson. It doesn't have an antiparticle. But the particle that we've measured may not be the standard model Higgs boson. And in fact, in theories beyond the standard model that we believe may exist, in which this standard model of particle physics is a lower energy theory that's embedded in one of these bigger theories, you could have multiple Higgs bosons. So you could have charged and neutral particles. So these are also being searched for in different channels. It's a very tricky thing to do, but given that we now have something that we've measured, it's kind of, along with understanding the properties of this object, it's going to become more of a topical thing to try and look for additional particles that could have similar properties.
If the particle's interaction with the Higgs field is what's giving it mass, then does it mean that our high school physics idea of mass being electromagnetic energy is now no longer valid?
No. So the mass that we're talking about for the Higgs field is at a different scale to the mass that you're talking about in this case. The Higgs field is an interaction with the very fundamental aspects of what are making up all of these objects that then do have the quality that you're alluding to. But each of their individual masses at the fundamental particle level, so the masses of these quarks that make up the protons and the electron, are coming through their interaction with the Higgs field, should it be a standard model picture of this field. So both of those can coexist, I think, as correct answers. It's basically different scales of how you're attacking the problem. Yeah.
Is there any connection between Higgs boson or anything else and dark matter?
At this stage, the Higgs boson, as it is in the standard model, doesn't do anything for us to explain what dark matter is. One thing that it is useful in that context, though, is we expect dark matter interacts via our normal matter every day by the Higgs interaction. So there's experiments that are buried underground, big detectors, looking for dark matter that might pass through the detectors, and they're waiting basically for these particles to exchange a Higgs boson as this kind of force carrier of the Higgs, and that recoil of some atomic nucleus would actually give us a signature of the dark matter particle. So there it's not so much that the Higgs explains anything to do with dark matter, but we can use the Higgs itself to look for dark matter. And it's especially reassuring that we know it's there now, so it does actually give us that a handle, at least on looking for dark matter. Yeah?
And the Hadron detector is the only place where the photons collide, or they collide all around the ring.
Yeah, so there are 4 experiments around the LHC ring where the protons collide. So the Atlas is just the one that we work on in Adelaide, so I focused on this because it's something that is dear to our hearts. But there's a competing and friendly competitor, if you like, at the opposite side of the ring that's called CMS. That's a general purpose experiment as well. There are 2 specific experiments that are at either side of Atlas, in a sense. One is called LHC-B, which is specifically looking for physics of the B quark, and another is called ALICE, which is to try and exploit collisions of heavy ions, which I didn't touch on, that we actually collide lead-lead ions inside the same Large Hadron Collider tunnel. So there are 4 experiments around the ring that are looking at the same data that we're showing from just one of them here.
Early on you alluded to symmetry. Mike, reading the internet about the Higgs boson, mentioned something that Peter Higgs developed the Higgs boson from considerations of symmetry breaking. Can you describe that simply, if it's possible?
It is, yes. I want to start in a classic picture that I teach in graduate classes, but maybe that's the right point. The thing is that, particularly the weak interaction, so this part that's responsible for radioactive decays and that, has this special property that the weak interaction only couples to, let's say, particles that are left-handed. So I should use my left hand. And so if you imagine an electron or some other particle moving along, then the polarization of that particle is in the direction it's moving. And so the weak interaction only couples to left-handed particles. Now, if you imagine this particle is moving along and it's got mass, then it looks left-handed. We could boost to another frame and accelerate so that we're going in this direction so that the electron actually looks like it's moving the other direction. And so if the particle's got mass, we can actually go faster and turn our left-handed looking electron into a right-handed looking electron. And then you'd say, but hang on, we've just said that this weak interaction that we had can only couple to left-handed particles. And so you've got this inconsistency in the theory that says, well, we can't have mass because we'd be able to accelerate our particles, and the choice on defining left and right would be dependent on the frame. And so what Higgs and the other authors did was formulate a particular way where we can kind of break what this symmetry is that says we still only couple the left-handed fermions with the weak interaction, but we can maintain that symmetry by kind of allowing our symmetry to take a different form. And the classic thing of what we have is a Mexican hat type picture. And so we've got a symmetry, if you imagine, sorry, Mexican hat, we're all sitting with our sombreros, and this thing, as we rotate around our head, it's got this circular symmetry, but at the middle, where everything looks kind of symmetric about it, isn't the point that our vacuum of nature prefers. We fall down, let's imagine it was gravity. It pulls a ball down, and we fall somewhere in the well of the hat. And that process of now we don't live in a vacuum configuration of nature doesn't live in the center where everything looks symmetric. We've fallen down, and when we have to kind of pick one spot on the bottom of this hat, and now if we look around us in any direction, there's some directions that look flat, and then there's kind of two directions that are going to look like they've got steep barriers in that direction. And it's kind of that kind of steep barrier that goes up in those two directions that kind of corresponds to what we call this breaking of the symmetry, and what will give effectively the Higgs boson itself, but also the way it interacts with our standard model particles, allowing them to have mass as well, but in a way that's still fundamentally consistent with this underlying gauge symmetry of how we formulated the theory in the kind of massless case. I need a rest now.
Yes.
I was wondering, when a Higgs boson decays into two photons, what happens to the inherent mass? Does it become converted entirely into energy, or where does it go?
Well, yes, it's entirely is that the energy of the two photons. And that's particularly what they're looking for in the bumps that Jack saw. You're taking the energy of those two photons and you're measuring the mass of that two particle state, and that's what the enhancement of the two photon signal at that mass is, the kind of your evidence that there was a Higgs boson that produced those two photons.
Let's go right at the back.
You said that you're not sure it's the Higgs boson yet, even though it's consistent with one. What are some of the other possibilities? Are there any that we know about?
So there are a few other possibilities. So to measure its properties, so the Higgs is a spin zero particle in the standard model. And so what this does is it gives you, imagine this case where you get the decays to 4 leptons. You get a lot of angles that come out of these leptons. You can measure a lot of angular properties with respect to each other. If the particle that they come from is inherently a specific spin, so a spin zero, the distribution of some of these angles in a certain basis will be able to tell you, if you have enough statistics, exactly the characteristics of that particle. So there are other configurations that a non-standard model Higgs boson could have, and so measuring these properties will let us know whether or not it's consistent with being the Higgs or not. Other specific types of things could be that this could be a Higgs from a supersymmetric theory, for instance, a composite particle made up of other things. And they would have different characteristics depending on what your favorite beyond the standard model theory might be. But by measuring these properties, you're able to actually pin down the characteristics of what the object you've seen through its decays is. Okay, that opened up a bit of a Pandora's box. This guy right at the back, he's been trying for a long time.
Why do you need the Higgs field to explain mass? Why isn't mass just a fundamental, just a property of a particle with light?
It is. It's back on that last question as I answered, because as soon as we got mass, then the designation of having left and right-handed particles becomes a frame-dependent statement, and we have the radioactive, the weak interaction in nature that is absolutely left-handed, and so we couldn't formulate basically a theory that's consistent with the weak interaction and the concept of, say, mass that automatically tells us left and right-handed particles are indistinguishable, and so we need the Higgs to kind of make the two pictures consistent with each other.
What's the sort of next candidate after the Higgs particle? Are there any sort of particles that people have proposed that we might be interested in after we've confirmed or found out what this one that we've discovered recently is?
There's many.
Just like, what's the future?
I should say to start with, I think it would be a fascinating thing if it were very boring, and Jack would hate to hear it, that if it's just the Higgs boson, this would be fascinating, that really kind of the simplest thing that you can really write down mathematically to describe the Higgs boson and solve these problems with introducing mass and still having a consistent formulation of the gauge theory. If that's all it is, And this does actually mean you've got a consistent theory that means there's no reason for this theory now to break down, to go from this energy scale, about the TeV we're looking at, can really run that theory all the way up to the Planck scale, so the distance where quantum gravity becomes relevant. There's nothing in this theory now that suggests that that there's anything inconsistent in how it's formulated. But this is, of course, the very boring scenario, because lots of money got spent on it, and if we started deciding how many dollars it was per particle that were produced, I mean, it might be, I guess, less exciting. And so as amazing as it would be if it's just the Higgs boson, I mean, there's a plethora of candidates of other particles, which, like Jack mentioned, supersymmetry and type things. I don't know if you want to comment. People talk about extra dimensions.
Yeah, so there are a variety of things. So one often talks about, and one of the reasons why we built the LHC was to try and look for something called supersymmetry, which essentially doubles the particle content of these particles that I showed early on in the talk. For each particle that you have in the standard model, you'd have a supersymmetric analog. So again, as Ross really nicely put about broken symmetries, supersymmetry would have to be a broken symmetry because we don't see equivalent particles at similar masses to the ones we measured from the standard model. But it has some very compelling features, particularly related to the Higgs boson, in a sense, to be able to keep its mass low enough to be able to measure. It also, from an experimental physicist point of view, doubles the amount of things we can measure, so that's really cool. And we can go and look for other stuff. But there's a lot of good reasons why we're interested to either confirm or deny this happening at the scale that we're creating in these experiments. So that's really, for a lot of us that are working on these things, the next smoking gun of particles to look for. And there's a variety of ways that you can break supersymmetry and give a different spectrum to the particles that might come out from there.
I was just wondering what the reason for smashing two protons together as opposed to two different sort of particles is.
That's a good one. So, yeah, the question was the reason for smashing two protons together as opposed to different types of particles. So for instance, the big collider that came before the Large Hadron Collider is called the Tevatron. That existed up until very recently at a collider facility just outside Chicago, and they were colliding protons and antiprotons. So the reason for them doing that was to get at specific types of things that you can have. The antiproton is made of antiquarks, so you're able to collide quarks and antiquarks and get very different types of properties that come out of this. The reason why the Large Hadron Collider doesn't do that is because to get antiprotons and cool them down and put them into bunches and accelerate them and then get them up to really high speeds is pretty tough to do. So, especially at the energies that we use. Basically, the proton is the easiest particle to accelerate up to these energies that we use. It's charged, you can bend it around in a circle. If you try to do the same thing at these energies with electrons, the electrons radiate energy in terms of photons. And you'd have to build a collider that would just be the size of the equator, I think, something like that, to be able to get to similar energies with a circular collider. So really the proton is the only object you have where you're going to be able to delve really deep into the constituents of it, and you can accelerate it to high enough energies to be able to do that.
You said before why. Whereabouts can this lead mankind in science with the applications? What can it do for mankind?
You mean the Higgs boson discovery, or
just
in general?
Technology, like, where is it going to advance mankind?
It's always tough to answer. I mean, that's partly what I was saying about just the idea of fundamental research for research's sake tends to just have good spin-offs. I mean, guys playing around with computers and figuring out how they can share information, coming up with the web, is quite a nice thing for mankind. We don't really know whether the Higgs boson or any other discovery from something like this will be a useful thing for ourselves in the future, or for any other fundamental research that we might undertake. But in order to get to these things, we've already solved some phenomenal problems with regards to materials to be able to build detectors that have spun off into industry and been used in a variety of applications. The accelerators I touched on being used in hadron therapy, among other things. So the spin-offs are always very hard to predict when you're really trying to push these areas of innovation. But they always tend to be there when you try and do something that no one's done before. There tends to be someone else comes in and looks at what you're doing and says, well, I could use that for my use case as well. So you just got to stay tuned, I guess, to see what happens.
We have two at the back. We'll let you take turns. One.
Is the Higgs boson a virtual particle like other force carriers? Call it a virtual particle or not?
Can be. But it's not the way we've created it here. So we've created it on shell, basically, which means that it's not virtual, it's a real particle. So it's been created and decayed to real particles. It's actually decaying to in the case of the Z bosons, it's decaying to one real particle and one virtual particle, because one of the Z bosons tends to be at the Z boson mass, which is about 90 GeV. But as we saw, if you have 125 GeV Higgs, 125 is less than 90 plus 90. So one of these has to be off shell, as we call it in the parlance. So this is a imaginary particle.
When it operates to get mass, does it do it as a virtual particle or as a real?
When the Higgs particle?
When it gives mass.
When it gives mass.
Yeah,
when it gives mass, presumably it's virtual.
It would be.
Yeah.
Okay.
Yeah, they go back.
Not directly related to the Higgs, but if you release a photon one at a time and you put it through slits like Young's, and you build up, your columns and stuff like that, and I hear that they're using larger and larger atoms, like buckyballs, collection of carbon atoms together as molecules and firing through slits. Because you're firing them at colliding them at such high velocities, and the masses are going up of these particles, have any experiments been involved in passing them through slits?
That's a good question. So in terms of these collider experiments and the photons we're creating from these, the answer to that, I think, is no. It could be done in principle if you know the direction of the photons that are coming off. You probably wouldn't do it with colliding two protons, though. What we do have, I mentioned this electromagnetic calorimeter, is that this is finely segmented, and it's the technology is chosen such that we can segment it to be able to measure an individual photon inside one cell. And that's a design choice, basically, to be able to contain all of the energy of a photon within a specific energy range that was driven by this discovery we hope to make, to be able to contain it exactly within these individual crystals. So it's not quite answering your question, but it's sort of a little bit related and driven some of the technology here.
So the heavier protons that you do up and you're doing lead and iron, is that to gain extra mass?
So the collisions of lead ions is to study something quite different. So it's essentially studying something called a quark gluon plasma, where you're interacting all of the constituents of these lead ions to be able to make a big soupy mess, to then try and understand the energy properties of this dense material that you make. So it's not really trying to do it's hard to say precision physics at these hadron colliders, but really it's more precision stuff that you do with the protons than with the lead.
Does the Higgs boson generate Higgs field like the electron generates an electric field? And if not, what generates the Higgs field? What is
No, yeah, it's very, very similar, but I think of it more as, okay, you have charges, the electric charges, and they generate, a surrounding electromagnetic field. All the particles that couple to the Higgs, so anything that's got mass, it has basically something that's like a Higgs charge, and then it means that these particles likewise have a field that surrounds them that's the Higgs field. I mean, the difference is the electromagnetic field, which is kind of described by carries photons, is very long-ranging. Photons are massless. The Higgs is very massive, and so the spatial survival rate basically of that field is very small, just because of this very large mass of the Higgs. But you can really think of it that we take an electric charge and we wiggle it. Classically, it just emits electromagnetic radiation. In the quantum case, the electromagnetic radiation are individual photons. You take a field or a particle that has a Higgs charge, and it has a corresponding Higgs field around it. And if you jiggle it, you can cause a vibration in the Higgs field, and classically it would be just Higgs radiation, but really in the quantum case it can correspond to a single vibration or Higgs particle. That's kind of quanta on that field.
We got some questions.
Sorry.
Oh, sorry. On a slightly different note, you sort of mentioned the extreme conditions that need to be maintained within the collider. I was just wondering, given that and given the sheer physical scale of it, what are some of the challenges, if there are any, of sort of maintaining the structure and maintaining the sort of the pristine experimental conditions within it? Do you sort of see challenges with keeping those extreme conditions?
So this is alluding back to the very low temperatures and the very clean vacuum that we have to maintain. This is the job of an entire division of people at CERN. So the low temperatures is a I would say relatively easy thing to do. It's well understood using liquid helium to be able to cool things to the temperatures we use, and quite a low temperatures below. Doing it on the scale that we do it is the big issue. So it really needs, each of these magnets that I showed, they're about 15 meters long, and there's on the order of 1,200 of them around the ring. They need to be as identical as possible and have very, very little problems. So when we first turned the LHC on, there were many problems, and it lasted only about 9 days. And then there was a very weak interconnect between some of these dipole magnets, and they basically ripped themselves apart. And what this caused is spewing a lot of this liquid helium into the tunnel, and it meant that we couldn't run for about a year after that, because it's so cold that if you want to make repairs to this, you have to heat things up to a temperature where you can actually go and do something there. And that heating up and then cooling back down again of something that big from such a low temperature and back to such a low temperature takes months. So from a practical perspective, you need to be sure that when you're going to cool things down, you've got them spot on. And again, from a practical standpoint, you really need to have things as identical as possible. So one thing I didn't mention is that we're actually going to have a shutdown of the Large Hadron Collider starting next year in about spring, which will last on the order of 18 months. The reason to do this is to be able to go into all of these magnets, and this is why it takes this time, to go to all of these magnets and actually repair a very tiny little thing called a splice on each of these. And what we found is through stress tests, we're not able to get the machine up to the energy that we'd like to be able to get it up, which is about double what we have right now. And so we need to go into all of these magnets after we've heated them back up again and put this little piece on there that actually holds one little small thing in place. But the problem is, if all of them have this issue, it takes a long time to do it. So the experiments, we're not lazy people. We're actually going to do a bunch of stuff during the shutdown as well. So for this detector that I worked on, we're going to insert an additional piece, an additional layer of measurement silicon inside this camera. So our camera's going to get even better during the shutdown. So we'll still be busy doing stuff during that time.
I hope this question doesn't reveal my terrible shortcomings in particle physics.
I hope the answer doesn't.
I was really interested in the question of why protons and why not other subatomic or atomic particles. And you alluded to the amount of energy and the sort of scale that current technology would require for the size of an accelerator to successfully collide electrons currently, because obviously they're much smaller. I'm just wondering whether there's been any speculation in the field, I mean the academic field, not the electron field, about whether that might reveal things that we don't already know about the constituent properties and particles of electrons, or whether that is sort of itself something that's already known.
That's an excellent question, by the way. So to give a brief bit of history, the Large Hadron Collider is colliding protons. In the same ring, there was a previous collider in there that collided electrons and anti-electrons. So the reason why it's a 27-kilometer ring is driven by the fact that there was an experiment there before that had a big ring with a big tunnel. So we use that for this new experiment. So the collision of electrons and positrons is a much cleaner thing. You can tune the center of mass energy you get to actually sit on top of one of these resonances. So for instance, I showed this Z boson resonance decaying to leptons. And the original collider that was in this tunnel was called LEP, and it sat exactly at that resonance. So it produced huge numbers of these Z bosons, and we got an enormous amount of information about that particle that we've then used in this Large Hadron Collider. The idea is that you have this sort of interplay of precision measurement equipment with discovery machines. So a discovery machine will kind of probe into a new frontier, and then you'll try and build a piece of precision equipment to be able to really understand that. So the obvious idea is that to try and have a collider that is centered on the Higgs boson mass, to be able to fully understand its decays, its properties, whether there's additional things that we can't see at the Hadron Collider because it's just such a messy environment that we have all this crap that happens basically, and we can't pick out potentially some interesting events that you could see if you collided electrons and positrons. So that's kind of an interplay that'll be being talked about for many generations of physicists to come, and hopefully will bear fruit in the next sort of 10 to 20 years. I'm being told we don't have much time left, so we'll take another question.
Okay. Well, the discovery of the Higgs boson, or the confirmation of its existence, reveals something about the nature of mass. But does it reveal anything about the apparent equivalence between the mass that causes gravitational attraction and the mass that gives things inertia?
I think the answer is no to that. Again, I think it's just on different scales. The fundamental mass of these smallest particles in nature aren't really responsible for the larger gravitational sort of idea of mass as we think about it in the classical term. So it's mass of a fundamental particle that the Higgs boson is giving to these things, which are described as Ross has really beautifully put in terms of quantum mechanical properties. These masses on a larger scale are described in terms of classical Newtonian properties. So the masses are somewhat different, I think. Okay, I think this guy's been waiting for a while.
A lot longer than the Higgs boson exists. Which is really my question. First of all, I'd like to thank you for a very lucid talk, probably one of the more interesting ones I've heard in physics for a long time. But you say you create Higgs bosons and then they decay. What timescale are we talking about?
That's an excellent question, actually. We didn't go into discussing timescales at all of any of these particles that are produced. Indeed, some of them, for instance, the B quark has a specific lifetime that you can use to be able to measure it. You can get a small displacement of the vertex. This thing I was trying to compare to a camera, we actually use to be able to do this. The Higgs boson, for all intents and purposes, it decays instantaneously after its production. The only way that you can probe different production mechanisms is by the different remnants that they will leave in the detector. So I talked about this one thing that was called gluon fusion, where we had these two particles coming together, a loop of stuff, and then a Higgs boson. You could have another type of production mechanism which splits your proton in two, has two W bosons that fuse to make your Higgs, and then these remnants from the proton can actually give you additional handles on measuring things within your detector. So this can give you a handle on the production mechanism. It doesn't tell you much about the lifetime, it doesn't actually get you to probe that vertex, but it can tell you, and the rate between those two types of measurements can really give you some interesting insight, again, coming back to these properties of the object we measured. The difference in these two types of decays or two types of topologies that you measure in your detector can really help you pin down and understand the nature of the types of things you've seen.
An interesting concept. it appears and disappears instantaneously.
Yeah, who knows if it was ever there. Okay, I think on that note, our boss is trying to wrap it up.
Please join me in thanking Paul and also Ross. A final note of housekeeping. The ladies' toilets are down the hallway that way, and for the male toilets go all the way down the hall, and then in the stairwell there's a door which leads to those. Thank you.
If it's fewer watts or anything.